Hey, you 11s, thanks for coming along. Hey, Zach, thanks for contributing on the chat. Can I just ask Imani, and Imani and Audra. Can I ask Imani and Audra just to contribute on the chat, just so I can mark you in on the register when you arrive? That would be grand. Imani and Audra. Can I ask Imani and Audra? There we go. It seems to be working okay. Let's get rid of that now. I popped out the chat and get rid of that. Cool. Oh, Imani's in. Okay. Imani's in. Let's now add Imani to that. Still no Audrey yet, though. Okay. Right, I will share my screen, guys. Share screen, share screen. There we go. I'll switch my camera to my clip cam. Whoop, whoop. On there. Boom. Right, let's continue with this paper, guys. Okay, so I've just got up to the end of question 8 with the other class, so please feel free to go back and watch the first half of this exam review, Year 11s. You guys are going to get the second half. Okay, let's continue. So, can I just ask a quick favor? If you guys, I've just done, there we go. If you guys can just let me know whether or not it's all working okay. Whenever I flip the tablet, I tend to get a small number of issues. Okay, so this diagram shows the displayed formula of hydrocarbons A, B, C, D, and E. Give the letters of the hydrocarbons to answer these questions. Which hydrocarbon is the main component of natural gas? It's going to be the smallest one, so that's A. Yeah, you may use letters, each letter once, more than once, or not at all. So, just for fun, guys, can you please, on the chat, can you name each one of these? So, just put them in order, A, B, C, D, and E, and then post them on the chat. It'd be fun for you to do it. Next, which other hydrocarbon is produced together with D when pentane is cracked? Right, so if I crack pentane, it's nice to do this in cracking. If I take 5 carbons, and I crack this. So when I crack it, by the way, what we're breaking is the carbon-carbon bonds. The reason why is because the carbon-carbon bonds are weaker than the carbon-hydrogen bonds, just so you know. Yeah, and we're going to crack this, and it tells us that we're going to form D. So we're going to split it here. Well, if this one now turns into the short alkane, yeah, the other one must be the short alkene. So we're going to form methane, ethane, ethene, propane, and butane. Well done, Tiff. Nailed it. Letters all messed up. That's okay. I get it. So we're going to be getting C as the other product. When the hydrocarbons undergo addition reactions with hydrogen to form B. Right, so we want to form ethane. This is an addition reaction. I haven't done alkene reactions with you guys yet, but just to show you. So if I want to make this one through a hydrogenation reaction. The word hydrogenation literally says hydrogenation, which means the addition of hydrogen. Hydrogenation. Yeah, the adding of hydrogen. Well, what could I have added hydrogen to make that? And the answer is ethene again. So if you take ethene and you add hydrogen, you will turn it into ethane. So we're using the same letter twice. Clever. Give the molecular formula of the empirical of E and them. Okay, so E is butane, molecular, C4. I'm going to switch to black. I don't want red. Suddenly realized. Yeah, sorry. I'm going to switch my pen to black. A, C, and C. Let's get rid of those. There we go. And the molecular formula for butane, C4H10, empirical. We can divide by, oh, Mr. Duncan, so should we start halfway or do it from the start? No, just start halfway through, Tiff. Just continue from here. Yeah, empirical, or you can do either one, Tiff. I don't care, whichever. So the empirical, we can divide it by 2, C2H5. Can't go any further because if we go to C1, we're going to end up with a fraction, and you can't do that. The definition of empirical, the simplest whole number ratio. So that one can't do it, so we're done. Hydrocarbons A, B, D, and E all belong to the same homologous series. Give the name of this. They are alkanes. The general formula, CnH2n plus 2. I like it. Draw the displayed formula of an isomer of E. Right, where's E? E is butane. There's only one isomer, guys. For butane, pause the video, have a go. It's only one isomer of butane. Can't move anybody around. You've got to break the chain. So there we go. And then I'm going to ask you guys to name it, please, because you guys are working at a much better level than any of my. I've just, whenever I get messages, I can't really check on my. Okay, that's fine. There we go. So, yeah, fine. 2-methyl propane. Lara is on it. Well done, Tiff. Good job. You guys are great. Right, 2 reactions that can occur when hydrocarbon A is burnt in air. These are represented here. Explain why different products is formed in reaction 2 and why this product is dangerous. Okay, so the first thing I'm going to say is reaction 2, just do bullet points, 3 bullet points. Reaction number 2 is incomplete combustion. There's going to be a mark for just those words. Incomplete combustion. Now we need to explain why it's happened. Well done, Sophia. Good job. This has occurred due to a lack of oxygen. Yeah, and now we need to explain why it's dangerous. Carbon monoxide is toxic. That will probably be enough, but it is nice to always give the reason. Binds to blood permanently, so oxygen cannot be carried. Can't be carried. It's nice to give the extra detail there. It's more biology, but I don't mind. 3 marks. I'll take it. Next. Aluminium and iron have some similar properties. Malleable, ductile, good conductors of electricity, good conductors of heat, high melting point. Choose 2 properties from the list that make iron a suitable metal for saucepans. Kind of makes sense. It's a good conductor of heat. It's a saucepan. You've got to cook in it. Good conductor of heat. There's no letters here, so good conductor of heat. And the other one is a high melting point. High melting point. Because you don't want to. Can you imagine having a pan that melted when you started cooking with it? It's a bad idea. Choose 2 properties of the list that make aluminium a suitable metal for power cables. Okay, so cables needs to be able to be drawn into wires. A cable it's been ductile, it's been stretched into wires. So makes sense. So ductile, and a good conductor of electricity. Power cables, good conductor of electricity. Now, what's really interesting about this question. I quite like what they're doing there, but I mean, if you don't know what a power cable is, you're a bit stuffed at that point. Can I just point out that question comes in a variety of sources, a variety of different types, because in reality, there are other properties of aluminium that make it more suitable for power cables. I wonder if they're going to do this. Not really. Interesting. Power cables. Power cables. These are your power cables. Yeah, these are your power cables. Well, okay, a good conductor of electricity and ductile, fine. But in reality, there are 2 other properties of aluminium which are much more important here. So if they said aluminium, the key reasons for power cables, and I'm happy power cables. Number 1, conducts electricity. Great conductor of electricity. By the way, the particle carrying the electricity in metals is the electron. Yeah. The next one is, yes, ductile. But the third one is it's lightweight. It's lightweight, low density. Yeah, lightweight and corrosion resistant. It doesn't rust because corrosion resistant. Because iron is also a good conductor of electricity. It is also ductile. So why do we use aluminium for power cables if we can just use iron? Aluminium is 10 times more expensive than iron. So why do we do it? Those are the reasons why we use it. Yeah, not the other two. Really silly that. But anyway, moving on. Okay, so we're dropping into alloys now. So steel is an alloy containing iron. These are three differences between steel and aluminium. Use the information of the list to suggest why steel is the better metal for making bridges. Okay? Steel is much stronger. Top answer. It's a bridge. You've got to drive over it. Yeah? We don't care if it rusts. Yeah? Much stronger. Use the information to suggest why steel is better. It's only 1 mark. Bridges must carry lots of weight, lots of car weight. Yeah? So steel being stronger, steel being much stronger is better. Don't think I'd quite like to drive over an aluminium bridge. I think it's a really bad idea. Use this information from the list to assess why aluminium is better for making aircraft bodies. Well, aircrafts need to fly, so it needs to be lightweight. I assume that's in there. Steel has a higher density. I like it. So, planes fly. Aluminium, less dense. So planes can fly further. I'm adding a detail there. Fly further, because you can actually make a plane out of steel. It can be done. It would be silly to do so, but it has been done in the past. Before aluminium became readily available, they used to just make it out of sheet steel. During World War II, they were making some amount of wood. Yeah, it can be done, but obviously planes are needing to fly as far as possible on a given amount of fuel. So planes can fly further on same fuel. Same fuel since lighter. Be interesting to see what the mark scheme says for that. That one interests me. Next. What is meant by the term exothermic? This is the thermite reaction. I like it. Exothermic, a chemical reaction. Yeah, it doesn't have to be chemical actually, but it's just a reaction. A reaction that releases heat energy to the surroundings. Nice and easy. Next, what does the reaction suggest about the reactivity of aluminium compared to iron? 2 marks. Well, if you look at the equation, aluminium is displacing the iron. Yeah, aluminium is being oxidized. Yeah, and the iron is being reduced. So it suggests, number 1, aluminium is higher in reactivity. By the way, you can't do that in your exam. You'll need to write the full word, just letting you know. Aluminium is higher in reactivity. Higher in reactivity compared to iron. Right, 1 mark. 2nd mark. How do we know this? Because aluminium is displacing iron from iron oxide. Done. It's displacing it. Fine. Next, which element is oxidized in the thermite reaction? So which element is gaining oxygen? Aluminium, obviously. No oxygen, lots of oxygen. So aluminium is being oxidized. Give a reason for your answer. Aluminium, is oxidized. Oxidized. Reason due to Al gaining oxygen. I'd write down all of those words, by the way, properly. I just figured I may as well keep it short, just to make the lesson a bit quicker. Okay, the reaction mixture is ignited. Oh, the thermite reaction can be used to join together railway tracks. The reaction mixture is ignited and molten iron pours from the bottom. The mold is removed and the molten iron solidifies to create a join between the two railways. Explain why the iron produced in the reaction is molten. Okay, bullet point number 1. The reaction is very, now notice I'm including this word here, is very exothermic. Yeah, they probably don't need it, but I want them to realize that I have some idea, some concept that in order to melt iron, I've got to reach crazy high temperatures. Iron has a melting point of about 1600 degrees Celsius. You know, to get that hot, that's bonkers hot. So it needs to be really exothermic. Second thing, so produces enough heat, so produces enough heat to melt the iron product. I like it. Done. Seems reasonable. I wonder if I want to say produce enough heat to get the temperature above the melting point. Yeah, enough heat to melt iron. I'm going to put in brackets, reaching a temp above melting point, MPT of iron. I know I'm putting it in a short form there. That's just like, it's me, I'm curious. That will be an interesting one to mark that. Right, cracking. What is meant by the term cracking? A chemical reaction. A chemical reaction that breaks a large hydrocarbon, into a shorter alkane and alkene. It's going to be an interesting one. Cracking, a reaction that breaks hydrocarbons into smaller pieces. Yeah. It's, by the way, it's also summed up by a thermal decomposition. So cracking and thermal decomposition are actually, they are the same thing. So what that means is a thermal decomposition is the breaking down of a compound using heat. Well, this is the breaking down of a hydrocarbon using heat. I'm going to add that on. It's going to be interesting that. Yeah, using heat. I'm tying that in because cracking is a type. Cracking is a type of thermal decomposition. And I realized that because the definition for thermal decomposition, a chemical reaction where you break a compound into smaller pieces using heat, yeah? And so this one is to break a, what's different is that this one is just to break a compound, yeah, using heat. And this one is just the same thing, but breaking hydrocarbons, yeah, breaking hydrocarbons using heat. So it's the same thing, but in a particular setting. Give a chemical test to show that the gas collector is unsaturated. 2 marks. Bromine water, you guys know this one. Bromine water, orange to colorless. Orange to colorless. Next, cracking is also carried out in industry. Give the name of the catalyst, zeolite. And the name of the and the temperature. Yes, please, that'd be lovely. Zeolite temperature 450. We're done. It's actually higher than that, by the way. It's a bit of a nightmare that, like, I always quote 450 in lesson. So no, I'm going to stick with that. The problem is it says industry slightly higher, 650. I'll stick with 450. It's what I always teach, so we'll see. Right, a sample of chlorofluorocarbons contains our empirical formulae. Love it. Contains carbon, 0.24 grams. Contains fluorine, 0.38 grams. And chlorine, 1.42 grams. Right, run the process. First of all, percent to mass. Oh, they've already done it for us. Thanks. Mass to moles. Divide it by 12. Divided by 19, divided by 35.5. We get all of these from the periodic table. P table, yeah. So on 0.24 divided by 12, 0.02, 0.38 divided by 19. Oh, surprise, surprise. That tells me I'm doing the right thing. 1.42 divided by 35.5. Oh, look at that. Divide them all by the smallest. Gotta love it. 1, 1, and 2. Final answer, CFCl2. Winner. Ratio. There we go. Next. The relative formula mass is 204. Deduce the molecular. Right, so how much does the empirical weigh? So the empirical, oh, I think you wrote 650 in the recent lesson. Did I? Did I write 650 for cracking? Did I now? Lara, I think you might be right. I think you might be right, Lara. Okay. Lara, let's make an adjustment. Let's see what the range is in the when we mark it. Be interesting. So if this is the simplest whole number ratio, how much does this weigh? 12 plus 19 plus 35.5 times 2. Let's do that on a calculator. 12 plus, don't do any maths in your head. I don't care how easy it is. Weighs 102. 204 divided by 102 is going to be worth a mark, equals 2. Molecular, that's going to be worth 1 mark, folks. If you do it in your head, you'll ruin it. So double it. C2F2Cl4. I like it. Should we draw it? That's, by the way, that there is a grade B at A level to name. I'd like my year 11s to have a go at naming that, please. That's AS level, and it's a grade B at AS. Lots of common mistakes here, folks. Lots of common range, mark scheme, 600, 700. Damn it! Oh, thank you. I knew I gave them. Sorry. Oh, I made my first mistake, I think. I didn't really want you to look at the mark scheme, but you, I gave it correct in lesson. That's all that matters. Thank you, Lara, for learning what I taught you. Anybody going to give me the name? Okay, let's see how many people get it right. So the really tricky part of this is that the chlorine and fluorine have the same ranking. What that means is when you number this, what you realize is because they're the same ranking, you can name it in either one, but you can't, because what's going to now happen is you now do it alphabetically, and the chlorine is going to come first. So you start off there. So it becomes 1, 1, 1, 2, tetra, chloro, tetrachloro, 2, 2, difluoro. Oh, look at this! Fluoroethane. How many people got their B? 1, 1, 1, 2, tetrachloro, 2, 2, fluoroethane. Well done, Lara. Well done, Libby. Difluoro. Yeah, Lara, you lost it. Tiff, well done. You missed your dash between the 2,2 and the difluoro. My third dash. Oh, well. Yeah, it's a really good effort. Well done. Right, let's keep going. So draw a dot and cross. I like it. The great thing is they've given us the displayed already. I'm going to switch to black. Carbon in the center. Chlorine, chlorine, fluorine, fluorine. In the gap, put a dot and cross because they're single bonds. Yeah, and then add all the people on. This is the most common mistake, is that people will walk away at that point and you lose the mark. What you now need to do is make everybody add up to 8. Yeah, most common mistake is that they forget these extra electrons. Fluorine also has it. The only one that doesn't add up to 8 is hydrogen, and the hydrogen always adds up to 2, so you don't add any of these extra circles on. We're done. 2 marks. Next. Name the type of bond that exists between the carbon atoms in all 3 structures. They are covalent bonds. Covalent bonds, nice and easy. Explain why diamond has a very high melting point. Susan, Boyle, sings, Nelly, the elephant. We know this question, guys, and we know it well. So the structure, diamond has, S stands for structure, diamond has a giant covalent structure. Covalent structure. Next, we're going to say what the bonds are. There are only covalent bonds. Covalent bonds in diamond. Next, strength. Covalent bonds are very strong. Next, the number of them. There are millions of these bonds. There are millions of these bonds. Energy. Lots of energy. Lots of energy needed to break all bonds. We're done. Done. Thank you. Moving on. Fluorine has a simple molecular structure. Explain why it has a low melting point. Susan, Boyle, sings, Nelly the elephant. Structure. They've already done it. Isn't that clever? It's nice to see that. Like, they're giving us the first one, hence it's less marks. So I'm still going to do it. Fluorine, I'm just literally repeating that sentence, is a simple covalent structure. Simple covalent or simple molecular, that's the same thing. Structure, I prefer simple covalent structure. Bonds, there are weak intermolecular forces, WIMPs, between molecules. You've got to say that, guys. Right, strength. These WIMPs, you can't write down WIMPs in your exam. You don't actually need to write it. You can just say intermolecular force. These are very weak. These are very weak. Save the writing. Right, number. There are very few. Of these forces. Energy. Therefore, not much energy. Not much energy needed to break WIMPs. Done. Moving on. Now, people are going to be sitting there going, oh my God, like, how do I know how many points to give? You don't. Do not ever ask yourself that question. If they ask you to explain a melting point or a boiling point, you are running Susan Boyle all the way through. Do not question it. Just run the process, get the marks, jog on. Suggest which theory is supporting evidence in the table. Okay. There are 2 theories explaining why graphite can act as a solid lubricant. 1, the forces of attraction between the layers are weak, allowing the layers to slide over each other. B, gas molecules are trapped between the layers, allowing the layers to slide over each other. First one's correct, the second one's garbage. The table below shows the ability of graphite to act as a lubricant at different locations. Earth surface, good. High altitude, average. Outer space, poor. How fascinating. Suggest which theory is supported by the evidence. Unfortunately, B. It's really annoying. Give a reason for your choice. So the answer is B. Yeah. B. And the reason being is, as you move from Earth's surface to high altitude to space, there is less air. There is less air. Seems reasonable? Not going to waffle there. I kind of want to. Less air, so as it becomes a vacuum, the air will leave the gaps, meaning that it won't slide as well. It's weird. Graphite and diamond can be changed from one form to another according to the equation. Would a low or high temperature favor the conversion of graphite? Give a reason for this. We've dropped into equilibrium, folks. Oh, so this is coughs. This is coughs. Knowledge. So this is temperature. The forward reaction is endothermic. So that's my first bit, is the knowledge, which is there. Forward reaction. And I know it's endo because it's plus. Yeah, forward. I'll do it in black so I can mark it. Forward reaction. Reaction is endothermic. Endothermic. Right, oppose. Would a low or high temperature favor the conversion? Right, so we want to go this way. So let's go. I want to shift this. I want to shift the equation. Shift left to right. I'll write it properly. Shift left to right. Right, by favoring the forward reaction. Favor, because that's what I want. Favor forward reaction, because conversion of graphite into diamond. We want to make diamonds. Favor him. Yeah, favor forward reaction. Right. So if I want to make the forward reaction faster, I do exactly the opposite. O stands for opposite or oppose. Exactly the opposite of endo. So I'm going to raise the temperature. Yeah. High temperature. So oppose. Increase temperature. Increase temp will cause equilibrium to lower temp. Lower temp. By favoring the forward reacting, shifting it left to right. So the answer to the question is high temps. High temp favor conversion to diamond. Favored. Yeah, fine. Interesting. Look at the mark scheme for that one. Annoyingly, I think that's just the answer. High temp favored. Yeah, but you've got to run coughs to get it. Next. Right, you guys haven't done this yet in my classes. We haven't done polymers yet. Spoiler alert. So, complete the table for the two polymers. Name, polyethene, structure of the monomer, structure of the polymer. Two carbons always go in the gap. Two long lines, put it in a square bracket, add N, add these people onto where they need to be. I'll even color code it. Two red ones go onto this guy. Yeah, and then these guys over here, I'll shrink my pen a bit, go onto this guy. There you go. And then one use of polymer, plastic bags. Plastic bags. Next, right, so water pipes. Yeah, this is polypropene, structure of the monomer. Right, put the double bond back. These are the two carbons in the middle. So I get rid of him and him. Put the double bond back and then just put the people on. So red, him and him. Yeah, and just put them on there in green, him and him, and I'm done. How easy is that? Name of polymer. Poly, brackets, propene. The poly means many propeins. Yeah, I like it. Water pipes are more usually PVC actually rather than polypropene, but whatever. Next, state 2 changes that occur in the formation of addition polymers from its monomer. Right, okay. So both of these guys as a monomer are gases. Yeah? So state 2 changes that occur. Monomer was a gas, and the polymer a solid is a solid. So a change in state. Change in state. Cool. Next one. The double bond's gone. Yeah. So carbon, 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 double bond in monomer breaks to form carbon, carbon, single bonds in polymer. Done. 2 points. Next. Addition polymers such as polyethylene are very difficult to dispose of because they are not biodegradable. State a reason why addition polymers are not biodegradable, do not biodegrade easily. They are very unreactive because all the bonds are very strong. Yeah, all covalent bonds are very strong. So difficult to break down chains. Unreactive. Next, you could also say that they're non-polar too, so they can't be attacked by water. You can also say that if you like. Burning and landfill. Burying in the ground are 2 methods of disposing of addition polymers. Suggest a problem with each method of disposal. So burning produces carbon dioxide, produces CO2, which contributes to global warming. Landfill, destruction of landscapes and habitats. Done. Question 15. We must be near the end by now, guys. Must be nearing the end. Yeah, nearly there. I think we're on the last one now. And it looks like a full-on calc, which is cool. A student made a solution of sodium hydroxide by dissolving 10 grams of solid sodium hydroxide in distilled water and making up to 250. Calculate the amount of moles. We're in grams, so number of moles is grams over rams. So moles equals grams, 10 grams over sodium hydroxide's MR. So sodium is 23, oxygen is 16 plus hydrogen. So, and by the way, you cannot leave it like that. Lots of students make that mistake. You can't do that. Yeah, the answer is 10 over 40. Yeah, bear that in mind. Do it over here if you have to. Yeah, 16 plus 1. And don't ever do anything in your head. Always do it in your calculator. I don't care what you say. So 10 over 40 gives me 0.25 moles. We're done. Amount of moles, so 0.25. So 1 mark for 40, 1 mark for the equation, and 1 mark for the final answer. Winner, grams over rams. That was easy. Calculate the concentration in moles per dm cubed of the solution. Right, number of moles equals C times V over 1,000 because we're in centimeters cubed, which was here. Yeah, so rearrange because they're after the concentration. Bring the 1,000 over, number of moles times 1,000, and then bring the V down over V will give me C. Input my numbers. 0.25 times 1,000 over a volume of 250 from the question. So 0.25 times 1,000 divided by 250, and I get an answer of 1 mole per dm cubed. It was 1. How interesting. 1 mole per dm cubed. Makes sense, I guess. Cool. Next. Take the reading at the start. So always remember that the students will read this one first because your eyes move left to right. Well, it's a trap, isn't it? Because the first one they ask you for is the end. Right, now everyone's going to make mistakes for this. So 26, this is 24. Yeah, we know in a burette we read top down, which is unusual. So this is 25 point. Well, sorry, that's not 24 at all. 25, 26, and each one of these is going to be 0.1. So that would be 25.10. Yeah, this would be 25.20. There we go. So there's my answer. And the key thing is everyone's going to lose that mark. Yeah, they're going to write down 25.2, but you can't when doing a titration. Because in a titration, you must, that number there, the second decimal place must be a 0 or a 5. You must remember that. So the first one, the end value is 25.20. The start, there's the trickier one. So this is 1.1, 2, 3, 4, 5, 6. So 6.5, and we're done. 1.65. The difference, take away the bigger from the smaller. 25.20 minus 1.65 gives me 23.55. And I'm done. Right, state the color of the methyl orange at the start and at the end of the experiment. So what were they doing? We know that methyl orange, you've got to know your indicators. Yeah, so methyl orange, yeah, methyl orange is red in acid, orange at neutral. Got to be careful, it's not orange enough. Yeah, orange very, very briefly. Yeah, orange at end point, and then turns yellow in base, in alkali. Yeah, so there's our methyl orange transitions. So the question says, where did it start? So what are we adding to what? So the student used sodium hydroxide solution to find the concentration of hydrochloric acid. He used a pipette to put 25 centimeters cubed of sodium hydroxide in the conical flask. Right, so the conical flask contains sodium hydroxide. They're then adding a few drops of indicator. So it's in alkali. So at the start, it's going to start off yellow. Yeah, it's going to start yellow. And at the end of the experiment, it's going to turn orange, because when it turns orange, you stop. They'll probably allow orange or red there, most likely. Why is the burette used instead of a pipette for adding the acid? Because a burette measures variable volumes. Burette measures variable volumes. And I think, yeah, cool. Next, sodium hydroxide reacts with carbon dioxide. Sodium moles per dm cubed is used. Calculate the amount in moles of sodium hydroxide. Oh, same thing. Number of moles is, there's my C, there's concentration, times by V, over 1,000. It's over 1,000 because I'm in centimeters cubed. So lob any numbers. Number of moles equals C, 2, times by a volume of 200, all over 1,000, equals 2 times 200. So it's just going to be 400 divided by 1,000, 0.4. So there's my answer. Nice and easy. Next, deduce the maximum mass in grams of carbon dioxide that can react with the sodium hydroxide. Okay, far more interesting. So we've just worked out that we have 0.4 moles of this guy. Well, look at the ratio between that and carbon dioxide. So the first mark here is the ratio. Sodium hydroxide to CO2 is a 2-to-1 ratio. 1 mark for the ratio. Yeah, then we can say, well, if that's the ratio, well, how much did I have? I had 0.4 moles of that guy. Well, to go from there to there, I just divide by 2. The most I can absorb is 0.2 moles. We're done. Oh, no, and then we've got to get to grams. Holy moly. So there's my moles of CO2. Right, next, number of moles is grams over rams. Right, so moles, I need to rearrange for grams. Bring rams over. So rams times moles gives me grams. Input my numbers. So carbon dioxide weighs 44.44. Yeah, carbon is 12, oxygen is 16, times 2 weighs 44. Times by 0.2 moles is going to say 0, divide by 2, 0.2 times by 44, and I'm going to be able to get rid of 8.8 grams and put that on the number. There you go, put it on the line. And that brings me to the end of the lesson. So let's now review it. Let's check it. Let's check it. Right. It's all there waiting. Right, switch to red pen. I think this is where I start. Yeah, there we go. Okay. ACC. Gotta love it. Molecular. Yep, thank you. Empirical. Yes. And then our alkane, CnH2n+2, and our branched isomer of methylpropane, or propane, sorry, well done. Incomplete combustion, insufficient oxygen, toxic, reduce. Oh, look at that, the M3 was my extra bit. Can you believe it? Toxic, reduces the capacity of blood to carry oxygen. Wow, I thought it was going to be the insufficient oxygen and it wasn't. That's just, what a stupid thing. Why is that on a chemistry paper? Stupid chemists. Next, a good conductor of heat, high melting point. I like it. Ductile, and a good conductor of electricity. It is stronger. It is stronger. 1 mark. Lower density, less dense. I like it. A reaction that releases heat to the surroundings. Heat, thermal energy is given out. Please note. Oh, it actually allows just the word heat. I hate that. Anyway, so. Next, aluminium is higher in reactivity because it displaces iron from iron oxide. Thank you. Next, aluminium is oxidized. It is gaining oxygen. Next, the reaction temperature reached is greater than the melting point. Reached a temperature above the melting point. I added it just as a little tack on. Ignore heat produced, lots of energy, ignore it. Wow, 1 mark was my tiny little bit tack on. And that was tricky, that's high temperatures reached, reject, probably. Accept, it's an accept column. High temperatures reached, so produces enough heat to melt the iron. I definitely got it, but I wondered if, interesting. Clever. Next. Large hydrocarbons become smaller ones. I like it. Chemical reaction that breaks down into shorter alkanes and alkenes. Bromine water. Decolorizes, turns, ignore, stark color and clear. What? Turns colorless, accept. It just says ignore the start color. So they just want turns color. That's okay. I've said colorless. I do get it. It is orange to colorless. Yeah. Decolorizes, turns colorless. But they prefer the word decolorize. Zeolite, accept zeolite. 450, yeah, better. Next. Ratio. Thank you. Divide all masses by ARs. Final answer. Yeah, got all of those. Double it. I like it by getting the number 2. Dot and cross. Q. Ignore inner shells. Yada, yada, yada. Covalent. Right. 4 marks. Giant structure, giant covalent structure. Still needed to say, yeah, I had to say it. Covalent bonds, many. So there are only covalent bonds. These are very strong covalent bonds, many of them. Yeah, lots of thermal energy to break. Yeah, we get all those. Fullerenes, intermolecular forces between molecules. Are very weak, little energy needed to break. Theory B, less gas as you move to space. High temperatures, ignore reference to Le Chatelier. Because, and since forward reaction is endothermic, like it, even though it's only 1 mark. Diagrams, yep. Plastic bags, top answer. Nice one. Polypropylene diagram. Ignore bond angle. Monomers join up, double bond breaks, increase in mass. Oh, they ignore state 2 changes from its monomers. Oh, they ignored my turning from a gas to a solid. Oh, I may lose a mark. Double bond breaks. I lose one. They wanted you to say small molecules join up. Okay, they didn't want more of a practical aspect. They wanted the chemistry bit. Okay, so there's my first loss for today. Yeah, they want us to say monomers join up. Add that onto my notes, definitely. Nearly there now. Produces CO2, greenhouse gas, carbon dioxide. All covalent bonds are strong and unreactive. Strong bonds, non-polar, are the exact both. Produce greenhouse gases and destruction of landscapes. Use up land, takes up space. New sites hard to find. Yep, I'll take it. Uses up land, takes up space. Right, that brings us, no, not quite, nearly there. 40. 0.25. 10 divided by M1. Yep, it's all good. Next, 1. I like it. Rearranging of the equation. Reading 25.20, 1.65, 55. Yellow, orange, or pink. Isn't that interesting? It don't allow red. Can be measured continuously. Graduous requires volume required not to be known. Ignore reference to precision. Pipette measures only one volume only. Different volumes can be variable vols. 0.4, the equation, and 8.8 grams ratio. Love it. That's the end of the paper. Right, guys, I hope you found it useful. I've just gone over the lesson. I'm going to leave you guys be. Have a great rest of your day. I hope you found it useful. I will continue to do as many of these papers as I can. That was a request from one of my subscribers. I hope you find it useful, and I'll see you guys all very soon. See you later, guys.